Hello, everyone. My name is Edward Graham. I am a professional engineer with about 30 years experience in the water resources field. And today I will be presenting methods to analyze stormwater controls to meet regulatory standards. The agenda that I've developed will include a brief description of a typical stormwater management standard, how to set multi-objective stormwater management controls, and then I'm going to run through an example of how to analyze whether or not a specific site or project will meet or not meet the standards. In other words, will it be in compliance or will not be in compliance? Let's talk about stormwater management standards. So typically the standards are set to address potential impacts due to changes in land use. The types of impacts can be listed as you see as normally the priority is flood control or flood protection. There's also urban flooding. So in the first case, flood protection is what we call a riverine flood protection. Second one is more in the urban setting, sewer surcharge and overland flows along the streets. You don't want that to go into your house, into your basement. There's also water balance, water quality, erosion control, and then there are standards for what to do during construction in terms of erosion and sediment control. And ultimately, there's also monitoring standards. I'm going to focus on just a couple of these, 4 of them in the example, just to see how multiple standards can be analyzed in one system to verify compliance or non-compliance. So when we design individual facilities, the criteria is often simplified based on simple input parameters defined by the upstream service area or downstream receiving waters. However, the effects must be analyzed at some point downstream, either at the outlet of where the changes are happening or further downstream, to verify that the standards are being met at the locations where the most vulnerable impacts or the greatest impacts and the highest impacts will occur. This is an example of a new draft standard that is being considered in Ontario. The Ministry of the Environment is going through a review of their standards. And the example here basically lists or shows the various criteria that they're considering. From left to right, you see water balance, water quality, erosion control, water quantity, minor and major system. That refers to the urban drainage. There's flood control that refers primarily to riverine flooding. And then there are last 2, construction and erosion control and monitoring. Those are at the beginning of a construction site. You have to have these controls. And monitoring normally happens before and after a site is developed to verify compliance or non-compliance. So I'm going to run, like I said, through some examples of how to plan or review a proposal, a site that is undergoing land development. So there's land use changes which will trigger changes in the stormwater response in an area. In this case, I'm going to look at 4 of the 7 elements in the criteria that we just covered. In this case, there's flood control, water balance, water quality, and erosion. These examples, you'll see some screens of a modeling tool. We're using Visual Hymo, which is a tool developed by Smart City Water. I've synthesized analysis into 10 steps. Step number 1 is to set the objectives and take those objectives and convert them to specific targets. that you can use to evaluate whether or not the standards are being met. Step 2 is to define the scope of or the extent of the analysis. Typically, a site that undergoes changes has areas upstream and also receiving channels or streams downstream as well. So we have to define how far upstream and how far downstream to look at the impacts of the development. Then we have to characterize both all the upstream and downstream areas as well as the site itself. Then we normally build a model that characterizes the existing conditions. That we're now in step number 5. Then we analyze the future conditions by changing the model in the areas that are undergoing land use change. We take pre-development areas and we increase imperviousness. We change the nature of those impervious areas to generate water quality constituents or pollutants that run off from urban areas. We look at the changes in peak flow, in volumes, and also the water balance of the site. So I've listed step 7, 8, 9, and 10 as the individual analysis that we're going to undergo or show. I will show you through this presentation. So step number 1 is to set the objectives, which sets also the direction for how to do the analysis. So in this case, there are policies, there are regulations, guidelines, there are previous studies, and then there are predefined water uses that establish the level of controls that are needed for this particular area. And again, we need to convert those objectives, all of this, through consultations with the various agencies into targets that we get. That again, we want to use those to establish baseline and compare future conditions with and without controls. So step 2 is to identify the scope or the extent of the study area. As you can see, this is a master plan project specifically that I'm using as an example, where the area within the red line is undergoing partial development or redevelopment. You can see from the green arrows, there's flows that go into the area, and from the red arrows, there are flows that come out of the areas into downstream receiving waters. Within the area that will undergo land use change, we have to define all the drainage features, both natural and man-made. That includes channels, sewers, stormwater management facilities, wetlands, LIDs. All of these have to be defined with enough detail to assess how the stormwater flows through this and what are the impacts in terms of attenuation and what we call the routing effects, as well as the water quality and downstream erosion impacts due to the amount of flow that is generated and the routing effects all the way down to vulnerable erosion locations. This basically shows the same area, the entire study area, with all the different data inputs that are required. The system takes all of these inputs and builds, and these are used to build what we call the pre-development model. So the model includes the areas, the imperviousness of those areas, the infiltration parameters, which are primarily the soil conditions, water table location, how high the water table is, the channel or routing parameters, the critical storm and continuous precipitation and temperature inputs that are going to be used to generate flows in the model. And then there are water quality parameters. There are primarily loading rates within each type of land use. Now, one of the big questions is whether or not the model needs to be calibrated. In many cases, yes. If you're trying to establish absolute values of certain parameters, such as peak flows, or critical water quality parameters, you will have to do some monitoring and sampling to assess what is coming out of these areas. But in many cases, we don't have to. We rationalize that the most important aspect of the analysis is to assess relative changes due to modifying the land uses and implementing controls. So I'm going to illustrate this through examples. And again, this is the first example. So I've taken one of the subwatersheds in the study area that you see, that we saw in the previous slides, and I'm looking at a specific smaller area that includes upstream development, what we call here the external drainage area 1, that goes into the external drainage area 2, that goes into an area that at the moment is not developed, but it is proposed for development. And the site that I've selected to assess impacts is immediately downstream of this development area. Those impacts will propagate further downstream, and under a complete study scenario, we will look at impacts all the way downstream or within locations that are especially sensitive to either flooding, erosion, or water quality as well. Conceptualize the analysis graphically. We would see a schematic such as what you see here. In here, you see the same external drainage area illustrated by this square with a tree that represents a undeveloped area or a rural area. Then we have another existing urban area. In this case, the ID is 63. I refer to that as the external drainage area 2. And then you see the area encompassed by the red rectangle, which is the proposed development area. In this case, it's under pre-development conditions. Then all of this combine and reach an outlet point that I'm going to use to assess impacts and whether or not we're meeting specific criteria or not. So again, going back to the area that is being developed, we see the external area 64, the external area 63. In the first case is rural, the second case is urban, going into the red area polygon that is proposed for development, and that goes to the outlet location. Now, this slide shows the layout, very conceptual layout of the proposed development. That is used, or a more detailed version of that is used to define the model parameters that represent the changes in the hydrologic response and in the water quality response in this area. So going back to the conceptualization in terms of a schematic, you see in the top rectangle, the pre-development conditions. In the bottom rectangle, we see the post-development condition, where the red rectangle, previously represented by one rural or undeveloped catchment, is replaced by two areas that are that represent the roof of the houses, as well as the remaining urban areas. Now, I've done this because the roof runoff is typically much cleaner than the remaining urban runoff. And we use clean runoff to recharge the groundwater. This is one of the greatest impacts of urban development, that the water balance shifts from the majority of the water being recharged into the ground or being returned back to the atmosphere as evapotranspiration. And we change that into most of the water running off. And the amount that runs off depends on the imperviousness of the development. So again, this slide just shows you in a little bit more detail the post-development condition without any stormwater management controls. And again, I'm using the receiving channel downstream to evaluate whether or not we meet the criteria or the proponent meets the criteria. In this case, I was not the proponent. So the next slide illustrates the different controls that the proponent was using as part of their design. The submission included these types of controls. In this case, you'll see a relatively simple treatment train where we take the roof runoff or the area number 1 going into a soakaway pit, typically on the side of the houses. Each house has takes part of the roof runoff because not all of it can be infiltrated, brings it into a soakaway pit, and some of it overflows during very large storms. Not everything can go into a soakaway pit, but anything that goes into the soakaway pit normally infiltrates. The overflow is when we exceed the capacity of the soakaway pit. We can exceed it upstream or within the storage area. This soakaway pit is an underground storage that once it's filled up, the stormwater basically bypasses and does not overflow. Does not infiltrate. At the bottom, we see the residential drainage, which is the roads, the grass in front of the houses, or in the back. Anything that doesn't go into the soakaway pits goes into the stormwater management facility, which you see here with the ID number 14. Both of these combine into the channel, and the downstream end of the channel is our evaluation point for this project. And again, the controls that are being proposed are shown in the green rectangles, and what we're evaluating whether or not those controls are sufficient to meet the flood control, the water quality control, the water balance, and the erosion control requirements. I'm going to start with the flood control, the peak flow control. In this case, we run the model, and with all the parameters defined in great detail, and we found that yes, the post-development flows without LIDs actually meet the pre-development flows. And LIDs are these soakaway pits that I was mentioning a few minutes ago. So we should be good with respect to peak flow control, and we evaluate this for the various storm return periods. Again, in this case, we ran right up to the 100-year storm. This actually shows the 5-year peak flow control being met. We have to do the same thing for the 100-year. And even though I don't have the results in this presentation, we will go through the very similar analysis. And if it doesn't meet the requirements, we have to go back to the proponent and suggest that they have to provide more storage in the stormwater management facility or more infiltration through the soakaway pits. Typically, quantity control for peak is achieved through attenuation, just because the much larger volume that is generated during the large storms. The next criteria is water balance. And again, there's various standards that are used for water balance. And in this case, we have to return the groundwater infiltration to the pre-development levels. So these results show the pre-development and post-development water balance results without controls. So post-development without any type of stormwater management control. You can see in the top pie chart a blue area that represents the groundwater recharge. In this case, 41% of the annual precipitation is captured into the ground and infiltrates. Some of it, 46%, actually, evapotranspiration is the greatest component where the rainfall converts into. Evapotranspiration is usually very high in areas where you have good vegetation, and 46% or 446 millimeters of the yearly total amount of rain is converted to evapotranspiration in this site. The groundwater, as I mentioned before, is 41%, and 13% of the rain is converted to runoff under pre-development conditions. If you look at the bottom right pie chart, you see that most of the rain is converted now to runoff. And this is one of the greatest impacts of land development, that you increase imperviousness and you are significantly shifting the water balance, which affects the sustainability of a lot of the channels and flood conditions downstream from this site. So for sure, there will be some controls required to maintain the groundwater recharge. In this case, the proponent, through the uses of these soakaway pits, which I'm going to illustrate in the next slide, maintains the groundwater recharge at 41%. You see here through this chart that the evapotranspiration is not returned to pre-development conditions, and it's practically, I'm not going to say impossible, because I guess anything is possible, but it's impractical or uneconomical to be able to achieve evapotranspiration similar to pre-development conditions. So there's been studies about blue roofs, green roofs, different types of LIDs that to enhance evapotranspiration, but it is a very difficult target to meet. So agencies recognize this, and they set the targets for development to at least meet the groundwater recharge, which removes a lot of the runoff and maintains the amount of the groundwater as a resource that we need for base flow augmentation downstream, or for basically replenishing the aquifers. Again, the runoff, the excess runoff will cause likely either flooding or erosion problems downstream, which brings us will bring us to the next analysis step. But before we get there, I just want to illustrate the type of soakaway pit proposed in this site. It is a fairly well accepted method of control. Is one of the low impact development technologies, or LIDs, and it requires a specific design where we introduce porous substrates below the ground to enhance the storage, and we have to take a look at the native soils as well to make sure that the rate of infiltration is sufficient to get rid of that water between storm events. So in terms of water quality, before erosion, we're going to talk a little bit of water quality, which is the third type of control. In this case, the standards are that we have to remove 80% of the post-development runoff pollutants. And in this case, we use two surrogate contaminants, indicative of loading of other types of contaminants. And those two contaminants are total suspended solids and total phosphorus. So again, the standards are to remove 80% of the post-development constituents measured as TSS and TP, total suspended solids and total phosphorus. So we undertake the analysis with visual HIMO. Again, this becomes a loading exercise based on land use. Land use produces typically an average loading per year that has been established from past monitoring efforts. And that gives us pre-development loading rates that you see at the bottom, in the bottom table, of 14.5 kilograms. These are per year of TSS from the pre-development area, and 0.107 kilograms of total phosphorus. You see, after the post-development without controls, the 14 kilograms converts into 212.3 kilograms under post-development without controls, that's TSS, and total phosphorus goes from 0.107 kilograms to 0.716 kilograms of phosphorus. This is a relative comparison between pre and post, and as we run the runoff through the stormwater controls that are being proposed, we see that the post-development TSS decreases from 212 to 36 kilograms, and the total phosphorus from 0.72 rounded up kilograms to 0.14 kilograms. I believe these are per hectare as well. So continuing onto erosion. So I mentioned before that stormwater management only achieves certain amount of infiltration. At least it meets the pre-development conditions. Evapotranspiration, we cannot meet the pre-development levels. So we have to meet the erosion control requirements downstream with the additional runoff that is produced and from the site, even after the on-site controls are implemented. So beyond on-site controls, we have to look at pipe facilities, and we do something that is active force of the water downstream, affecting the resistance of the soil to be dislodged and be transported along the channels. And there are specific criteria that are established by agencies. In this case, would be in Ontario would be a conservation authority, or the Ministry of the Environment, or the Ministry of Natural Resources. So the greatest of all the criteria are used as a standard. Again, for this, there's a need to go out in the field, do some surveys, and assess the properties of the channels to identify the location that is most vulnerable to erosion. The analysis using VO or visual HIMO basically enters a lot of the information that characterizes the area upstream, the channel itself, and the controls to evaluate the erosion threshold, or I call that an erosion index that accumulates over a long-term analysis. So you take several years of rainfall data, you run it through the model, and it produces attractive force that is applied into the channel downstream at the most vulnerable locations. And we compare this attractive force under the different scenarios, development scenarios, the pre-development, the post-development without controls, and then the post-development with controls. And in this case, you see three curves that represent exactly that: the pre-development, the post-development without controls, which is the red. So pre-development is green, the post-development without control is red, and you can see that the attractive force applied, or the cumulative erosion index, increases from the green line to the red line, and then the proponent has to do something to reduce the cumulative attractive force that the channel is exposed to. And in this case, they implemented stormwater management, flood control with extended detention, sufficient storage so that most of the storms, peak flow, and other flows below the peak are reduced to quite a bit lower than post-development. In fact, we have to go, in this case, below the threshold erosive strength of the soil, so that we minimize the amount of dislodgement and transport of sediments downstream. So in this case, they met the erosion control standards, and these four analyses illustrate how we can evaluate whether or not the certain standards are being met or not. Again, as a summary, in Ontario, where I practice, the emphasis is on a flood control, water balance, water quality, erosion control, major and minor system capacities on the streets and in the sewers, construction, erosion, and sediment control, and monitoring. LIDs are heavily emphasized nowadays because, yes, they provide great reductions in stormwater at the source, which is the upstream in the treatment train. They are distributed within the areas that are undergoing development. So, and they are absolutely necessary to be able to reduce the volume as well as increase the amount of infiltration into the ground. And finally, tools such as visual HIMO, or there's other tools in the market, can be used to analyze pre, post without control and post with controls, so that we can compare and evaluate whether or not we're meeting the standards. So with this, I just want to open it up for any questions. Thank you.